Hello. This week I'm going to look at some other aspects of orogenic wedges and origin theory in general. This will be a series of smaller podcasts that'll make up the entire suite for the week. So the first thing I'd like to talk about are doubly-vergent orogenic wedges. We saw this last week when we were looking at sandbox models where an orogenic wedge was built by deforming a pile of sand, but this was done with using a plastic sheet underneath the layer of sand that went down through a hole in the table in order to build a doubly-vergent wedge that had no backstop, or rather the backstop was then flat lying like this. Sand would then pile up on top of the horizontal backstop. This is meant to simulate a kind of subduction process like we see over here on the right, where the substrate of the lithosphere, that is the lower part of the crust or the mantle, is going down into the lithosphere and scraping off the upper part of the crust. This might be as little as the sediment layer, or it could include much of the crustal section as well. But together then they build up this orogenic wedge that may be back thrusting over the upper plate and thrusting out in the front. In the sandbox models, we saw that in fact we would build a taper, a critical taper in the sand, where it would have a rather low taper angle. That is what we then refer to, according to critical wedge theory, as the minimum taper out here on the downgoing plate. But on the upper plate, it was steeper, and in some cases it actually had two angles, kind of a minimum taper and a maximum taper. And I showed that in the sandbox model. You can go back to last week if you want to see that. Now what this implies is that there is a polarity to the subduction or to the orogenic wedge system that's driven by the polarity of the subduction. So because this is not symmetric, one plate is going down underneath the other, the resulting structures are also not symmetric. And we can see the difference then both in things like the taper angle, but also the deformation paths. That's what these little arrows are showing, is the particle paths of rock as they move through the wedge, either through growth or if there's erosion coming out of the top. So this asymmetry then becomes a characteristic of the subduction process. And we have a terminology we sometimes use for this to reflect this asymmetry, and we talk about the pro-wedge and the retro-wedge to refer to the two sides of the system, pro-wedge being above the subducting downgoing plate, the retro-wedge being the back thrust zone over the upper plate. And this asymmetry then in the structure is reflected in the topography, which is, you can see at least in this cartoon version, is asymmetric, in the structures, which tend to be steeper and have a steeper ascent path, if you'd like, or particle path in the thrust sheets in the retro wedge compared to, say, the toe of the pro wedge, which tends to have overthrusts of relatively low angle. But it also has some implications for things like the foreland basins. So in a doubly-vergent system like this, we have foreland basins on each side. This is still a load. It's still going to flex down the lithosphere, both plates of the lithosphere, and it's going to create then a foreland basin on this side, which you might refer to then as the retro foreland basin, and also on this side, which is then the pro foreland basin. And the overall system then, we have then this system where we can look at the mass fluxes in the system. We have an accretion of material, which is this FA, that's an accretionary flux into the wedge, and an erosional flux out the top of the wedge. And somehow then those are going to balance in order to give us the size of the overall wedge system. And that eroded material is then going to go back into the foreland basins that are on either side. Here's an example of this kind of a system. This is the Pyrenees, where if we go from south to north, you can see that the Iberian plate has been subducted underneath the European plate. It's actually stopped today, so it just went under a little bit being a few hundred kilometers perhaps, and then it stopped. But that was enough that it then grew an orogenic wedge up above this suture zone. That wedge is doubly-vergent and asymmetric. So we have a pro wedge out here that is coming out into the Ebro basin, which is the foreland basin on the Spanish side. And we have then back thrusting zone onto the European plate, onto the French side, where we have the foreland basin, which is the Aquitaine basin. So looking a little more at the structures, we can see that this is in fact a fold and thrust belt in the South Pyrenean zone, and it thrusts right down into the Ebro Basin. And this would look much like the front of the Alps and the Molasse Basin, for example. On the other side, we again have a flexural basin. In fact, the Aquitaine Basin is much longer. It's not a lot deeper, but it's much wider. It's been a more uniformly flexed downward, and I'll explain that in a moment. And then again, back thrust along its margin here. We can look at things like the subsidence path to try to see what that tells us about the loading of this plate. Now, what's interesting about the foreland basins is, again, depending on the symmetry of the subduction, their architecture can be very different. And in particular, if we contrast now the pro-foreland basin, the pro side and the retro side, during the growth of the orogenic belt and the convergence that takes place, we can see that the pattern of deposition must be very different. And the reason it's different is because the pro wedge is sitting on top of a subducting plate. That subducting plate has some velocity, and it's actually moving down and going underneath the orogenic belt. That means that as it's moving, the flexural profile will also be moving. In fact, it'll be sort of largely staying still in space in response to the loading of the mountain belt out here, but the plate will be moving through this profile. And that means that the sediment that's deposited sequentially in the basin will have this progressive onlap onto the downgoing plate. Right? So think about what's happening to a plate or point on the plate here. It's moving through subduction. It's moving down underneath the system. As sediment is deposited and say just filling in that gap, each younger layer will come a greater distance out onto the plate. All right? And that's true whether it's either growing or when it reaches a sort of steady state. By that, we mean that the load is not getting any larger with time. It's staying largely still in terms of its magnitude, but this plate is still moving with respect to the load. So we still get this progressive onlap of the sediments. And in fact, many of the sediment, the sedimentary section, if we were to say, look out here, you don't even find the older sediments because the migration of this bulge in the basin has now moved out here, and we no longer have these older sediments preserved here. Now contrast that with what's happening on the retro side of the belt. Over on this side, now we're on the upper plate. The upper plate is not being subducted, meaning that it's largely, at least in this reference frame, it's a bit of a reference frame question, but in the reference frame of this plate, it's not moving. This is a pin. That's a nail that indicates that nothing is moving here, at least not the boundary between the other plate. The boundary with the other plate is fixed. And that means that although the load is growing as the mountain belt grows, so the mountain belt is here between the two figures somehow, right? The mountain belt can be growing and that load getting larger and larger, but it's not migrating horizontally with respect to this plate. And that means that the flexural bulge, which is out here, is going to always be in the same place with respect to the mountain belt. Mountain belt's getting larger. There'll be a little bit of back thrusting, but aside from that, it's largely staying fixed with respect to the load. And the profile will get deeper with time. The basin flexure will get deeper with time, but it won't migrate. And that means there is little to no onlap of these sediments that are filling the fore deep here. So we have these two different stratigraphies. This is, again, the steady state and the growth phase, but we have these two different styles of stratigraphy, one with no onlap, here with onlap. Here it's simply getting deeper with time. Here it's getting both deeper, but it's also migrating. The depot center is migrating towards the peripheral bulge out here. And this can be summarized in these sort of chronostratigraphic diagrams. If you've not seen these before, this is looking at this is a representation of time and distance for the foreland basin system, where it's really marking what is happening at any point in space and point in time. And what we're seeing is, for example, along here is the migration of the thrust front. So this is the thrust front at today. So the top of this diagram is the modern, and that thrust front was located further and further back into the mountain belt with time. So it's as we go down, that's going back in time, then it looks like this. The foreland basin at any point in time is represented by this hatchet zone here. right? So this had an onlap onto the basement. This is an unconformity. This is the, say, the pre-orogenic stratigraphy you'd like. That's the stratigraphy that's exposed here. There's some kind of unconformity that was occurring when this was the peripheral bulge or outboard. We maybe had some erosion. And then the new sediments were deposited on that surface with some kind of an onlap. If we look at the other side, we find again that this pattern is quite different. We have some back thrusting. So here's the thrust fronts. Here we have some back thrusting with time into the basin, but then it largely just stays steady. What that's indicating is, say, this thrust front here doesn't really move after some point in time. That's the sort of steady state argument that this, if the load's not getting bigger, the mountain belt's not getting bigger, then this is not going to propagate further into the basin. It's going to largely be pinned at this point. And then we simply fill in the basin, but the region that's being filled is almost constant in width. The bulge is not migrating. There's a little bit of curvature here during growth, but that's about it. This is the peripheral bulge with time, again, going downward. It largely stays fixed, and we're simply filling that in with space. So we have these two very different characteristic, what we refer to as basin architecture on either side of the mountain belt, that's reflecting whether we're in a pro side or the retro side of the system.